Hi all, so we're looking at chapter 9.4, which is dealing with hypothesis testing, um, how to conduct a hypothesis test for a population mean, the 4 steps for hypothesis testing. Firstly, you would state your hypothesis about the population parameter. Again, emphasis, the population parameter. Okay. Then you would prepare and choose a significance level and test statistic, check conditions and assumptions. Compute a test statistic and p-value. And finally, interpret. Do you reject the null hypothesis or not? What does this mean? Probably one of the more difficult things is to interpret the rejection of the null hypothesis. If you wanted to see what actually goes on when you compute a test statistic for one sample test, this is the actual formula, where the test statistic is x bar, the population mean, the sample mean minus the null hypothesis divided by the standard error, and the standard error has to be calculated separately. If conditions hold, the test statistics follows a t-distribution with df equal to n minus 1. This is all done by technology, so we don't really use this formula. There are 2 conditions, of course: random independent sample and large sample. The population must be normal, or the sample size must be at least 25. Okay, those are the main conditions for using hypothesis testing. Short discussion about one-sided and two-sided alternative hypothesis. Just as with hypothesis tests for proportions, hypothesis tests can be one-sided or two-sided depending on research question. The choice of the alternative hypothesis determines how the p-value is calculated. And here's a demonstration. If it's two-sided, we put equal for the null, not equal for the alternative. One-sided to the left, always equal for the null, by the way. HO is always equal. One-sided left, the alternative would be less than the null, and one-sided right, the alternative would be greater than the null. Here are the instructions for calculating test statistic, the t-test, the hypothesis test using the TI-84. I will demonstrate that when we get into the problem. In the 2010 season, average home attendance for NHL hockey games was was 17,072. Suppose a sports statistician took a random sample of 30 home hockey games during the 2014 season and found a sample mean of 18,104 with a standard deviation of 1,203.5. Can we conclude the mean attendance at the NHL hockey games has changed since 2001? Let's examine this using statistical analysis, okay? We're not going to look at this broadly and try to make a determination. So in 2010, the average home attendance was 0.72. Now, it's asking us to not change. Not change mean if we were using a hypothesis test, we would pick a two-sided hypothesis test, equal to or not equal to. In other words, it hasn't changed. So let's see how they did this problem. First, they hypothesized that the U value, the hypothesis is 17,072, or not equal to 17,770. Prepared a random independent sample. Sample size is large, assuming the population is large, and then we used the technology to find the test statistics. So I want to show you how to use the technology to do this. and how they got this answer. Okay, you would go to StatCrunch, open up stat, tstat, one sample with summary, and then you would go ahead and type your numbers in. So the sample mean here is 17,000. I'm sorry, the sample mean is 18,104. The sample standard deviation is 1,203.5. Go back here to the problem. I'm missing a number. Oh yeah, the sample size. The sample size is 30. Oh, I lost my sample size is 30. And then where it says hypothesis test, we would type in the original population, which was 17,072. By default, it puts in the not equal to for the hypothesis test. Okay, and compute it. And this should, of course, match what we have already. Yes. Let's open that snipping tool and compare it. Put it next to what they have here and see if it's exactly the same. I'm gonna have to drag it in here. Let's see if that works. Sometimes there's only so much you can do with technology, right? Okay, here we go. And you can see what's happening here. It gives the t-stat, the p-value is less than 0.001. Now, if we wanted to do this with the calculator, you can also do this with the calculator. Go to your TI-84, stat, scroll over to test, and we're taking number 2, t-test. We're inputting stats. Okay, so the U is 17,072. For this, the 2014 values 18,104. The standard deviation is 1203.5. The sample size is 30. Select not equal to and calculate. And here we go. So we get the t-stat, and we get, this is FYI. I'm going to have to explain this in a second. Capture the screen, bring it over, copy, and place it in here. Okay, let's place it here and then drag it over. Okay, so values are similar. You can see that the t statistics is 4.6967. And if you notice, the p-value here is given as to 5 zeros. In other words, that's the p-value there is 0.00058. That's what that e to the negative 5 power means, E889, which is 0.0001 to 4 decimal places, okay, which is what we have here. So a little more work when you're using the TI-84 calculator. Now, draw your conclusions. Since the p-value is less than the significance level of 0.05, right, 0.001 is less than 0.05, we have to reject the null hypothesis. Yes, the mean of the attendance at hockey games has changed since 2010. Of course, we could see that, from the data. You can actually see that it changed, but this is showing it statistically. Okay. If the alternative hypothesis is two-sided, a confidence interval can be used instead of a hypothesis test. Both approaches will always reach the same conclusion. So let's get right into some of the problems that we have here. This question here has a printout from a T-stat calculation already, and all we're trying to do here is to answer the question. A health agency suggested that a healthy total cholesterol measurement should be 200 milligrams DL or less. Records from 50 random random and independent, from a study conducted by the agency showed that the results in the technology output given below test the hypothesis that the mean cholesterol is more than 200 using a significance level of 0.05. Okay, so the null hypothesis we know would be equal. The null hypothesis would be equal, and now we're checking more than 200, so greater than for the alternative hypothesis. From our printout here, the t-stat is 1.46. And the p-value is 0.075. So since the p-value, remember 0.075 is greater than the given here is 0.05. So since the p-value is greater than the significance level is greater than the significance level, greater than 2. Do we reject or not reject? What do you guys think? Right. Do not reject if it's greater than. Do not reject. Do not reject. There is insufficient evidence. We don't reject the null hypothesis. We keep the null hypothesis. In other words, there's insufficient evidence that the mean cholesterol level is more than 200 milligrams per deciliter at a significance level of 0.05. Very big, broad statement. All right, now we're actually going to compute stuff. 30 GPAs from a randomly selected sample of statistics students. Oh, I'm sorry, I skipped 11, no? Yes, I did. I skipped 11. Where is 11? All right, there is 11. Okay, there's 11. Here we go. In a country A, the population mean for 3-year-old boys is 39 inches. Suppose a random sample of 15 3-year-old boys, so n is equal to 15, from country B showed a sample mean of 38.6 and a standard deviation of 3 inches. The boys were independently sampled, so the condition and normally distribution, so the two conditions are met in the population. Determine whether the population mean for country B is significantly different. Doesn't say less than or greater than, just different. So we're looking for not equal to 39. Okay? Remember, the given mu is equal to 39. Now, to find the t statistic and the p-value, we would need to put these numbers into StatCrunch, right? Oh, by the way, they're asking for not equal to, so we're going to select number A, not equal to. So we want 39, 38.6, 3, and sample size 15. Let's do this first with StatCrunch, and then we're going to do it with a calculator, yeah? So tstat, one sample with summary. The sample mean, let's type in our sample mean is 38.6. Standard deviation is 3. Sample size is 15. H is equal to 39, and automatically puts in not equal to 39 unless you changed it, okay? It's already selected for not equal to 39. And compute. So let's copy this and place it over. And I'm also going to do the calculator part so you can see what's happening, yeah? So let's put this into our notes. Okay, then we want to do the calculator as well, just to make sure, because some of you will be using the calculator, right? So again, to do this, we press stat, test, number 2. So the input, we're inputting statistics, not data. So we're not using a table. In this case, U0 is 39. X bar is 38.6. Standard deviation is 3. Sample size is 15. Not equal to is already selected. And calculate. And hopefully the two match, right? If it doesn't match, then it would mean that I did something incorrect. So let's go ahead and check our results here. I'm going to put this one here as well. Technology is not behaving today. Okay, paste. All right, so we've got our two results. Let's compare. From both of these, you could see that the t-stat, the two decimal places, is negative 0.52. Okay, negative 0.52 and negative 0.52. So the t-stat is negative 0.52. Forgot the negative sign, negative 0.52. And we see from both of this that the 3 decimal places, the p-value is 0.614. Now, immediately we know that 0.614 is greater than the significance level given of 0.05. That means we do not reject the null hypothesis. Do not reject the null hypothesis. There is no reason to believe that 39 is not the population mean at the significance level of 0.05. Okay, there's no reason to reject that null hypothesis. Remember that null, we're saying that the null hypothesis is not equal to 39. Now, they're asking us to change, for part B, change the sample to 30 boys instead of 15. So we're going to go back to our 2 data sets and just edit. We're not going to fix a whole lot of stuff here. Options, edit, and instead, the only thing we're changing is the sample size to 30. And compute it. Copy this. You can stick it over here. Okay, and let's also do the calculator part where we can edit with the calculator part. Yeah. Can we edit this? Let's see. We go back to stat tests. Remember, your old data is still stored in there, so the only thing you would need to change is the 30. Yeah. Enter, enter, enter. Okay, what is wrong with this thing? Here we go, enter. All right, so we're going to capture this screen here, bring it over, and we should see the same results for both, yeah? All right, so both show the same result of negative 0.73 for the t-statistic. And the p-value in both cases is 0.471 to 3 decimal places. So again, 0.471 is greater than 0.05. So we do not reject the null hypothesis once again. There is no reason to believe that 39 is not the population mean. Same answer as the previous part A. No reason to believe, even at an increased sample size, there's no reason to believe that 39 is not the population. Explain why the t-values and p-values for part A and B are so different. So the answer for this is kind of obvious. A larger sample size causes a smaller standard deviation error, narrowing the sample distribution. Remember that little slide I showed you with how they calculated it? With less area in the tails as shown in the smaller p-value. In other words, for the p-value for the smaller sample was what is it, 0.614, 0.614, and the p-value for the larger sample size is 0.471. So 0.471 is gives a smaller tail areas. Okay, so that is why the parts A and B are so different. Yeah. All right. Now, what happens if you have an insane amount of data? Of course, you would have to consider using StatCrunch then. In this case, you would have the click down button to put this data directly into StatCrunch. If not, you'll be typing this into a table with the calculator and trying to, making mistakes when you type it in. So you're going to use that little button, that click icon, and it's going to give you an option to open in StatCrunch, and it's going to take all that data and transfer it directly to StatCrunch. Now, the 30 GPAs from a randomly selected sample of statistics students at the college are given in the accompanying table. Assume that the population distribution is normal. Okay, so random and normal distribution, the conditions are met. The technician in charge of records claimed that the population mean GPA for the whole college is 2.84. Okay. A one-sided test with a significance level of 0.05 had previously been performed on the data, and the null hypothesis was rejected. Use the data to find a 95% confidence level for the mean GPA. And then it continues, if a two-sided alternative had been used with the significance level, would the hypothesis means have been still rejected? So first we need to compute the confidence interval. I hope you guys can remember how we do that. So I already moved this data into a table. I asked my lab to move it to the table, and I'm going to first get my confidence level. So stat, tstat, one sample with summary. Sorry, I did that wrong. Stat, tstat, one sample with data. Var is 1. Okay, select var is 1. And we want the confidence level. Okay, so it's going to automatically compute that, right? Compute it. Let's copy this and paste it over. All right, so we've got the confidence interval here to two decimal places is 2.96 and 3.22. Okay, now it's already next test the two-sided alternative. Okay, so H is equal to 2.84 and not equal to 2.84b, two-sided. So now we're going to go back to the same data and perform another test. Okay. Okay, close this one. Stat, t-test, one sample with data, var is 1, and we're doing a hypothesis test now for 0.84. Is it 2.84? I'm sorry, 2.84. Okay, notice it automatically puts in the not equal to 2.84. Compute it. Just think, you would have to put all of this data in a list in the TI-84 and do the same test if you wanted to. I'm giving you an easier alternative here to simply use StatCrunch for this. What's the point of having technology, free technology with your program and not using it, right? All right, so we've got some data here. We're going to go ahead and kick this in here, more data, and see if we get what we want out of it, yeah? Technology is very finicky today, but yeah, we'll get what we want here. Okay, here we go. So the test statistic is to how many decimal? Two decimal places, 3.86. The p-value to three decimal places is 0.001 if we round this. So notice immediately that 0.001 is less than 0.05. Since the p-value is less than or equal to, number one, less than or equal to, okay, reject the null hypothesis. This means that there is sufficient evidence to conclude that the mean stats is different from 2.84. If we reject the null hypothesis, which is saying that it's equal to, then we're going with the alternative hypothesis view that there is evidence to conclude that it's different at 2.84. Yeah? All right. Um, Hypotheses are always statements about, so hopefully you guys were paying attention in the notes. Hypotheses are always about population parameters. Which of the following measures the test statistics? The test statistic is simply how far away from the observed mean lies the hypothesized value of the population mean. Okay, I think that's all the questions that you have for this section. So let's go ahead and conclude this video.